Alright kiddos, welcome back. I want to continue talking about periodic properties. We just finished a video on ionic radius, and I actually want to conclude that with a comment or two related to some negative ions. So I want to look at these three negative ions to begin this video. It would be nitrogen 3 negative, oxygen 2 negative, and fluorine 1 negative. And you can see that the radius of these ions decreases as I go from nitrogen to oxygen to fluorine for their negative ions. Now, if I look up their atomic numbers, so nitrogen's is 7, oxygen's is 8, and fluorine's is 9, that tells me how many protons and electrons the neutral atom has. So protons for nitrogen would be 7, oxygen would be 8, and fluorine is 9, and electrons. Now for the neutral atom of nitrogen, it would have 7 electrons. But since it's 3 negative kiddos, it would have 10 electrons, wouldn't it? Right? Have 3 more negatives than it would have positives. Oxygen has 8 electrons normally, but since it's 2 negative, it would have 10 electrons, wouldn't it? And fluorine has 9 electrons normally, but since it's 1 negative, it would also have 10 electrons. So we say that these three ions are isoelectronic to each other because they have the same number of electrons. And hopefully this will help explain why their ionic radius decreases when we go from nitrogen's radius, nitrogen 3 negative, to oxygen 2 negative to F1 negative. So even though they have the same number of electrons, do you notice that they gain protons when we go from nitrogen to oxygen to fluorine? So nitrogen only has 7 protons, attracting those 10 electrons. Oxygen has 8 protons attracting those 10 electrons, and F negative has 9 protons attracting those 10 electrons. So the more protons, the more positive charges you have in the nucleus, the more tightly you can hold these 10 electrons, and so it should make sense that the radius would get smaller for those ions when you went from nitrogen to oxygen to fluorine. Okay, next up I want to talk about ionization energy. And so to form a positive ion, folks, an electron must be removed from a neutral atom. This requires energy. Now whenever we use the term requires energy, we can use a synonym for that, which is endothermic, and we're going to be using that term quite a bit this year. That means energy is required. So to take an electron away from a neutral atom, energy is required. It's an endothermic process. The energy is needed to overcome the attraction between the positive charge of the nucleus and the negative charge of the electron. So ionization energy is defined as the energy required to remove an electron from the gaseous atom. Now I want you to think of ionization energy as an indication of how strongly an atom's nucleus holds onto its valence electrons. A high ionization energy value indicates the atom has a strong hold on its electrons. Atoms with large ionization values are less likely to form positive ions because it's hard to take away electrons. And remember, to make a positive ion, you've got to take them away, and if the ionization energy is high, it's hard to remove that electron, so they don't form positive ions very easily. Likewise, a low ionization value indicates an atom loses an outer electron easily. So if its ionization energy is low, it's pretty easy to take that electron away, so it can lose it easily, and it's likely to form positive ions. So let me give you a couple of different extremes here. So let's look at our periodic table. Let's look at sodium and chlorine. Now one of these two is likely to lose an electron easily. The other one, it's really hard to take an electron away from it. Can you guess, or can you think about which one might be easy to take an electron from? Well, let's find out. Sodium's atomic number is 11 and chlorine's is 17. So let's go back to our notes here. Sodium has 11 protons, and chlorine, way on the other side, has 17 protons. Okay, now electrons, sodium has 11 if it's neutral, and electrons, chlorine has 17 if it's neutral. Let's write down the electron configuration for both of these. Sodium is 1s2, 2s2, 2p6, 3s1. Chlorine is 1s2, 2s2, 2p6, 3s2, 3p5. So, it looks like they both have electrons in the third energy level, right? So, which one would it be easier to take an electron from? The atom that has electrons in the third energy level with 11 protons attracting them? Or the atom with electrons in the third energy level with 17 protons attracting them? That's right. If you said that sodium is more easily able to lose an electron, you would be correct. This would have the lower ionization energy. It's easier to take an electron away from sodium than it is from chlorine. Remember, they both have electrons in the third energy level, right? But sodium only has 11 protons attracting those electrons in the third energy level. Chlorine has 17. And if you remember, when I go from sodium to chlorine across a period, doesn't the radius decrease? And when the radius decreases, kiddos, that means the electrons are held closer to the nucleus, and therefore they would be more difficult to remove. So when I go across a period, the radius decreases and the ionization energy increases. So chlorine would have the higher ionization energy. Okay? Now, what about when I go down a group? Well, let's take a look here. We were just looking at sodium to chlorine. So let's look at this chart here, which is the first ionization energies of the elements in periods 1 through 5. We were just looking at sodium, and we finished up at chlorine here. And you can see that when we went across from sodium to chlorine, the ionization energy increased. And remember, that's because the atomic radius decreases. Now that's true, as you can see from this graph, for any period on the periodic table, from lithium to neon. Let's take a look at where that is on the periodic table. Here's lithium, folks, right up here. Let's clear this so it's a bit easier to see. Here's lithium, and here's neon. So when I go across from lithium to neon, folks, remember the radius decreases. We're gaining protons without gaining energy levels. The radius decreases, and if you look at this chart from lithium to neon, the ionization energy increases. It becomes harder to take an electron away from lithium to neon. So when the radius decreases, the ionization energy increases because the atoms get smaller. Now, what about when I go down a group? What if I go from lithium to sodium to potassium to rubidium to cesium? What happens when I go down that group? Well, let's look at our graph. When I go from lithium, let's use a different color here. When I go from lithium to sodium to potassium to rubidium, let's see. It's sort of hard to see because I marked this up, but lithium's ionization energy is about 500, and rubidium's, you can see, is lower than that. And sodium's is also lower than that 500, and so, or potassium's was, excuse me, and so is sodium. So you can see when I go down a group, the ionization energy decreases. Notice that's also true with the noble gases. When I go from helium to neon to argon to krypton to xenon, doesn't the ionization energy decrease? So, when I go down a group, folks, the ionization energy decreases. Can you come up with the reason why? Why does the ionization energy decrease when I go down a group? Yeah, you're right, because when you go down a group, you are gaining energy levels. Lithium has 2 energy levels, sodium has 3, potassium has 4, rubidium has 5, cesium has 6, and francium has 7. When you gain energy levels, doesn't the atomic radius increase? So the ionization energy decreases because the radius increases. It becomes easier to take an electron away from atoms whose electrons, valence electrons, are farther from the nucleus. Alrighty. So, why do you think noble gases have such a high ionization energy? Now, don't use the phrase because they are stable. A lot of kids like to say that. But you can notice that when I go across any period, the noble gases have the highest of all ionization energies. Here, let me erase the marks all over this graph here. You can notice, kiddos, that when I go across any period, from hydrogen to helium, from lithium to neon, from sodium to argon, from potassium to krypton, from rubidium to xenon, when I go across any period, the noble gases always have the highest ionization energy in that row or in that period. Why? That's right. If you said because their radius is the smallest in a period, you are correct. And that's tough for kids to get a hold of. When you look at the noble gases, kiddos, remember the noble gases are to the far right of every period. And when you go to the right across a period, the radius always gets smaller. And so if those electrons are closer to the nucleus, they're harder to remove. Their ionization energy is higher. Why do you think the alkali metals have such a low ionization energy? So once again, if you look at your graph and we take a look at the alkali metals, do you notice that in any period, the alkali metals have the lowest of all ionization energies? Yeah, and from lithium to neon, lithium's the lowest. From sodium to argon, sodium is the lowest. The alkali metals always have the lowest ionization energy. Can you think about why? That's right, because their radius is the largest in a particular period. And so since those valence electrons are so far away, they're more easily removed. So the ionization energy is lower. Okay, let's try a few problems. So we're going to use our periodic table for this. So, which element has the smaller atomic radius between letter A, lithium, and nitrogen? So we need to look at our periodic table here. Let's clear the page, and let's find lithium. Let's see what they are again. They are lithium and nitrogen we're looking at. So here is lithium, here is nitrogen. So the question is, which one has the smaller radius? That's right. If you said nitrogen, you are correct. When you go across a period, the radius gets smaller because we're gaining protons without gaining energy levels. Okay, you try B and C without my help. Decide which of each pair has the smaller radius, then come back to the video and see how you did. Okay, welcome back. Your next choice was between krypton and neon. So krypton and neon. So let's find those on the periodic table. Here's krypton, here's neon, which would have the smaller radius. So remember, kiddos, when you go up, the radius gets smaller, or you could say when you go down, the radius gets bigger, right? So neon only has 2 energy levels, krypton has 4, so neon would be your choice for the smaller radius in letter B. Okay, and then cesium and lithium. So cesium's right here. It has 1, 2, 3, 4, 5, 6 energy levels. Lithium only has 2 energy levels, so I hope you chose lithium in that pair. All right, number 2, which element has the larger ionization energy? Remember, if the ionization energy is high, the radius must be smaller. That's right. because the electron's closer to the nucleus and therefore harder to remove. So we're going to choose between lithium and nitrogen. Remember, nitrogen was the smaller one, right? So since it's the smaller, it would have the higher ionization energy. Krypton and neon, since neon was the smaller, you would expect it would have the higher ionization energy. And between cesium and lithium, lithium is the smallest, so it would have the higher ionization energy. So hopefully you can see how radius and ionization energy are related to each other. When one goes up, the other goes down. Or you could say when one goes down, the other goes up. They're inversely related to each other. So that's our last question. Explain how atomic radius and ionization are related to each other. So as atomic radius increases, ionization energy, the energy needed to take away an electron, decreases. Okay? Alrighty. Hopefully you were with me on that. When we see each other next time, we're going to be talking more about ionization energies, and we're going to focus on something called the first, second, third, fourth, and higher ionization energies. So stay tuned for that. See you then. Bye-bye.